Hello, this is Mark Unkefer, and welcome to the Fiber Optic Sensing Association webinar toward 1 billion sensors, distributed fiber sensing in a pervasive IoT context. This is a presentation of our technology committee. Our technology committee is truly one of the how shall I say, crown jewels of our association, our secret sauce. They have done an extraordinary amount of work, and these webinars are an opportunity for them to share some of their work product. In this particular context, while DFOS has been a problem solving in many industries, in rail, pipeline, in-well monitoring, with the emergence of smart city application, we have DFOS really playing an opportunity, having the role of playing a large part of the sensors in that infrastructure. So to our presenters today, we've got two, Etienne Rochat of Omnisens has worked in the industry. He worked at that company since 2004. He's an author of more than 50 papers and has 10 patent families. It's each 10 patents arrayed in a number of jurisdictions. He will be joined a little later by Chris Minto. Chris was the opening chairman of our technology committee and is part of the founding team at Omnisens. He is a PhD in physics and a member of the Institute of Physics and a chartered engineer and chartered physicist. And he has been also in the past a very effective chairman of our committee. So now we'll start with Etienne. Thank you very much for your presentation.
And thank you, Mark, for the kind introduction. So the purpose of today is to address what could be better than 1 million sensors. And to do that, I'm going to describe a little bit what fiber optic sensing is, how it works, what we can do with that. I will illustrate with a couple of examples from the field, and then we'll try to see how we can move from 1 million sensors towards 1 billion sensors. Again, illustrating that with the potential growth we have in the dark fiber network worldwide. Also what FOSA members have been doing already today, and also what is related to the growth of the 5G network with the related fiber backbone in the background. So let's begin by introducing fiber optic sensing. The general concept is to work with the interaction of light being sent down an optical fiber and what is surrounding the optical fiber itself. For instance, we are going to send a pulse of light down the fibers, and there will be a little bit of light which is backscattered from the fiber towards the optical interrogator. The quality of the light or the signature of the light which is backscattered will be influenced by what is happening along the fiber. The backscattered signal is, for instance, sensitive to strain, deformation, sensitive to temperature or to local vibration. And by using that analysis of the backscattering light, it's possible to get an information on the surrounding condition of, in this case, the pipeline. There are multiple families. We'll look after today distributed temperature sensing, DTS, distributed acoustic sensing, DAS, which is looking at vibration, and mainly distributed strain sensing, which is looking at deformation, elongation, compression. The key features basically is that there is a single fiber along the asset that we use with the light, and everything is starting from the interrogator and then just follows the fiber. 24/7 continuous monitoring over that long distance, and virtually thousands of sensing points with typically meter-size localization along the asset. The sensors are passive, so along the fiber there is no need to add anything to the optical fiber itself, no need for power, no need for a sensing head or whatever. It provides a large variety of measurement. We talked about temperature, about strain, about vibration. We could think of humidity, we could think of radiation, and others. We could also combine those different sensing technology along the same optical cable. And also what is extremely interesting is that it's upgradable. So by having a fiber along the asset guarantees that in the future we can upgrade the instrument only whilst keeping the sensor and make sure we benefit from the most recent advance in the technology. As illustrated there, the fiber optic cable is buried or laid along the asset, pipeline, railway, larger structure with the centralized optical interrogator somewhere. Many things we can do with those fiber optic sensing technology. Pipeline condition monitoring, that one field. We can look at heat tracing of a thermally insulated pipeline, application in third-party intrusion and security, making sure that only the people who are entitled to be there are somewhere in the right of way, for instance. Application in geotechnics, looking at soil and ground movement, traffic, rail monitoring, many activities in oil and gas in-well monitoring, looking at process monitoring as well, bunch of application in structural health monitoring, large structure, let it be dam, bridges, walls, and also large application in power cable monitoring, aerial, terrestrial, and subsea. Some example of what can be done with fiber optic sensing along a pipeline for safety application, and seeing at what are the important points. It's very reliable. A ruggedized interrogator, just a simple fiber optic, and it being passive, little can go wrong with that. It's essentially safe. Again, due to the fact that it's a passive sensor, often dielectric, you don't have issues with electromagnetic compatibility, you don't have issue with exposure environment, for instance. You need electrical power only at the interrogator position and nothing elsewhere. It's essentially secure. The fiber is often buried or fixed, attached to the asset, or installed in aerial condition. If someone comes and tries to mess around with the fiber, you quickly notice that it's economical because basically a single interrogator is capable of covering a very long distance. So if you look at the cost per sensing location, as unbeatable, and it's also easily scalable, and it scales similarly to the telecommunication market, so in that sense relatively easily. If we look more specifically for the pipeline, in terms of condition monitoring, we can find leak, single phase, mixed phase, also detection of subsea leak. In terms of security, we can guarantee that there is no intrusion or unexpected intrusion in the right of way, and therefore detect hot tapping, valve thefts. We can look at perimeter security around pumping station. Also some activities in subsea pipeline monitoring related to security with anchors and fishing gears. In terms of geotechnics, looking at earthquake detection, that's one component. Other are related to soil erosion, with, for instance, water coming to the pipe, subsidence monitoring resulting in potential deformation of the pipe. Likewise, landslide that could just get everything away and break the pipeline. In the process monitoring, looking at slackline monitoring, slug profiling, peak tracking, also the technology allows to follow the pig as it is moving along the pipeline, so very efficient way of following that. Pipeline deformation, making sure, for instance, related to a landslide, that the pipeline is not deformed too much, looking potentially at hoop strain, that could be a signature related to the pipeline becoming thinner at some point, and also looking at the trace monitoring for thermally insulated pipeline and making sure that there is sufficient heating power in the system to maintain the fluid in a good condition. So how does the physics in the background work? Basically, we send that pulse of light from a laser into the fiber. We look at the backscattering coming back. We go to an optical detector and we do the analysis. This is what we see on the left-hand side of the figure. From there, we will distinguish three backscattering mechanisms known as Rayleigh, Brillouin, and Raman, named after the people who discovered them a few tens of hundreds ago. When we look at Raman scattering, we have a signature which is related to the thermal excitation of molecules. So it's a response mainly to local heat. If we look at Brillouin, the signal is related to the thermal excitation of vibration within the lattice, and it's sensitive to both temperature and strain. And if we look at Rayleigh, it's mainly a change in the index of refraction on the fiber, and that is sensitive to the vibration, the heat, and the strain. So basically, by looking at one of the other of those technologies, or by combining them, we get access to vibration, deformation, and temperature according to what the needs are. Just a little note, Brillouin is sensitive to both temperature and strain, sometimes referred to as DSTS, as a combination of DTS and DSS in our terminology. Some example from the field. First one is traffic monitoring along a freeway, which is related to acoustic monitoring. And as example, we can see on the screen information related to the instrumentation, things like the average speed of the traffic, potentially looking at traffic jams or traffic being stopped, potentially related to an accident, always with a localization. So there's always the link between what is happening and where is this happening. On the bottom right-hand side, we see at a deeper level into the raw data, some lines, some tilted lines in the figure. And looking closely, we could surely see cars coming into the motorway and then exiting the motorway, overspeeding car with the lines which are a bit too much to the top, and slow traffic with nearly horizontal line. So that would be an example of looking at traffic using the optical fiber laid along the freeway. Another example is the monitoring of a subsea power cable. In this example, an 88-kilometer offshore cable with instrumentation on both sides, so linking an onshore substation to a offshore platform, looking at hotspot and thermal bottleneck along the cable, at managing dynamically the load, at looking at the burial depth variations along the cable, and potentially looking at the localization of electrical fault along the cable. And the bottom right figure is showing the temperature profile along the full length of the cable, and you could see, okay, I was expecting temperature to be constant. No, it's not, and it's just reflecting difference in the depth of burial, difference in the seabed condition, and to some extent different in the cable itself. It can be deployed over long distance, up to about 100 kilometers, and goes well for AC and DC cables. Geohazard monitoring, looking at landslides. An example on the left-hand side with a cable where an elongation of the fiber up to about 0.4% was measured, which is extremely large for the fiber, and that land deformation was built up about a month or so. What was interesting, and this is what is shown on the figure, top picture, not much to be seen, mainly things are moving underneath, and bottom picture, after some work has been done to stabilize the landslide and make sure that it has no impact on the pipeline. Another example of geohazard monitoring is soil erosion due to water ingress. So there is, as seen on the right-hand side picture, an opening in the ground, and then water is penetrating there and can start moving the soil, the backfill, and eventually get to the pipeline and start having problems there. And this was seen basically because suddenly there was a drop in temperature along the pipeline at a very localized position related to water coming in. Further analysis also showed variation in the day and night temperature that you normally don't have when you are buried in the soil. An example of leak detection, in this case methane, along a pipeline with less than 0.5% of the flow which is leaking, so much less than what you would have in a mass balance system normally, showing a thermal signature, as we can see on the bottom right picture, with a cold spot and maybe with some artifact or other thermal dissipation on the side. What is interesting there is that the temperature difference was below 2 degrees when the leak was picked up, and it shows also that leak detection, especially when the leaks are extremely small, so at the very beginning of the leak, takes a long time. But bear in mind that large leak with respect to this detection would be detected, for instance, by a mass balance system. Interesting demonstration of pipeline product theft using distributed acoustic technology, a case in South America with a known issue along a pipeline of people coming and stealing the feed, identified by mass balance, so a lack of volume, and some knowledge that the thefts were coming with a regular pattern in the middle of the night. The pipeline was instrumented temporarily using the optical fiber, and we see on the top pictures a few signatures of what is happening along the pipeline, with some orifice noise related to the fact that oil is being extracted, and then some noise related to the opening and the closure of the valve. Key is that the system was capable of detecting the illegal operation by the valve. That was confirmed by the customer because nobody was supposed to be there, could relate that 5 times the fluid was extracted, and eventually, due to the localization, you can do something and protect the pipeline. Another example related to distributed temperature sensing, which is fire detection in tunnels. An example in Beijing, where about 70 miles of track are being protected by fiber against fire. So the key is to detect quickly and to localize accurately where there is a fire. Alarming in less a minute using different technologies in the background, very cost efficient due to the distributed nature and the centralized interrogation unit, very reliable, a lot of certification in the background, with a lot of installation in Europe and Asia on this. And an example on the way that the information is displayed to the operator is the geographic information system on the right-hand side, basically a map with the temperature distribution and, in case of a fire or an alarm, the position of the fire, which is related there for fast intervention. Acoustic monitoring, again, looking at train tracking, for the time being for non-vital application, but it allows to identify train within about 10 meters, depending on the position of the fiber along the track. And basically it brings information live on traffic management, information in relation to whether a train is late or so on. So customer relation, and it's the beginning or the demonstration of what could be done further using distributed acoustic sensing technology on railroad application. On those rails as well, it's possible to look at the condition monitoring of the asset. For instance, looking as shown in the figures at rail defects, at subsidence in the track bed, as potential overhead electrification issues, at problems with rolling stock like flat wheels, which are going to make a noise along the fiber and can be identified. Another application related to geotechnology and distributed acoustic sensing is Rockfall on train line. In this example, there was rain, large major landslide going on, and that was detected thanks to the acoustic signature. And then it's possible to warn the people on the track and prevent accident by the landslide position. Another example related to a track defect with noise which is coming regularly, always at the same position all the time, which is a signature of something which is not correct, and the time difference is related eventually to the axle spacing and speed. So that's a way of understanding that something is happening there. Can be related to a railhead defects or even a rail brakes, poor quality in the joints, missing fixing, the ballast which is damaged, having voids, or other issues related there. Smart cities is interesting because it's promising for the future of our sensors and possibly reaching our billion sensor target. Smart city is a city where there is a lot of digital technology embedded everywhere to enhance livability, workability, sustainability. That's one definition. Another one joins smart city, smart economy, smart mobility, smart environment, smart people, and eventually smart living and smart governance. So it's a kind of how it could look in the future when we get the technology together into the city and try to extract most of that. An example about intelligent traffic. If we look at the current state in Charlotte, there are a few points with fibers, not enough yet to work with intelligent traffic, for instance. But if in the future we start having more of those fiber nodes, then it becomes possible to deploy sensor everywhere. Intelligent traffic that becomes possible. You can do speed monitoring. You can do vehicle identification, accident avoidance. Would help surely for autonomous cars and autonomous train. Interesting for smart grid and the way you handle transport of energy. You could look at how the road infrastructure is maintained or being affected, damage, and eventually you can monitor the asset and protect the asset. So all that would be related to the fact that we have a backbone of fiber that we can use for our monitoring system. What is interesting is that the fiber goes everywhere, and because we can combine the interrogation system along that fiber, it becomes possible to follow different activities. So you could look at fence security in a specific area of the smart city, but you can look at a pipeline crossing the city for some reason and leak and security around that. You could look at right of way, at traffic, at peak tracking or whatever, having different console providing the relevant information to the different operators. So all that combined on that centralized optical network. You may say, is that easy to deploy? Essentially, yes. Most of our sensing systems are related to telecommunication like cable. For instance, as an example, the single jacket all dielectric with a few tubes, each having a few fibers, which is laid in a conduit, or more or less similar size, maybe with a bit more armoring, a bit more stiff and robust, double jacket, all dielectric, which can be directly buried. Also a single steel tape armor cable, again for direct burial in the ground. All these are standards from the telecommunication, or we are going to adapt them slightly but marginally to what we do. So things related mainly to temperature monitoring and to acoustic monitoring will be made with those cables. And then for some specific conditions, we have tight buffer cables, meaning that the fibers are locked inside the cable, and then the cable ultimately will be locked into the structure to provide good information on strain, deformation, potentially on acoustic signature. I have to say that mainly those systems are working with single mode fibers, which are those from the telecommunication. Raman DTS are working with multimode fibers, but that's the only one working with multimode fibers. Example of using the fiber as a sensor inside the tunnel and along those tracks. So having the fiber as close as possible to where you expect the signal to be, in this case sound, acoustic signature, using as much as you can the existing communication cable, which is laid in a little conduit by the track, and handle the different position when necessary. Installation, direct burial is preferred in most applications, again very much common from the telecommunication world. And then in some typical sections like a tunnel, you may wish to have the optical fiber in a different position. So you adapt a little bit the installation to there. Normally, we always work with new fibers along a new project. Retrofit is a bit difficult yet, though we are working on that. If we look at the pipeline, usually the cable is laid together with the pipeline in the trench, at the bottom of the trench, sometimes level to the top of the pipeline. That's a very common installation method. It is also possible to install the sensing fiber into a conduit, an HDPA conduit, which is along the pipe trench. Advantages is that the cable can be installed once the pipeline is completed, so less disturbance to the pipeline lay and to the rhythm of pipeline construction. But the HDPA conduit is a kind of attenuator for the signals that we try to measure, so it's not as optimal as a direct burial. Retrofit along a pipeline is rather difficult, but there again, people are trying to find a solution. Where are we today? And I think it's about time to give the mic to my co-author, Chris, for the second part of the talk. Chris? And while Chris is being unmuted, I can comment on that FOSA global sensing map. So basically, this shows where the FOSA members have been, status 2017. We have altogether reached more or less 1,300 installations worldwide, covering about 32,000 kilometers of sensing fiber.
Hi there. Good morning, everybody. Apologies for being a little bit late there. Apologies also, I have a little bit of background noise where I am. I've just got off a plane. I found the quietest spot that I can, so hopefully we'll be okay. But if we've got any background announcements, I might pause for a few seconds. Thanks to Etienne for covering the technology aspects of this talk. I think he's done a great job of showing the origins of the technology, how it can be deployed, and some really exciting case studies that have come from the members of FOSA. It's really worth remembering that FOSA as an organization is really only, we're into our second year right now. And the technologies here have reached a stage of maturity pretty much after about a decade of development. And so what we've seen there is the immediate sort of early adopter approaches where people have had a need and the technology has provided an immediate solution, most often in a sort of retrofit scenario where fiber already exists and has been adapted to use, but occasionally in, unique bespoke deployment applications where fiber, particularly for strain monitoring, for example, has been deployed to suit. What we're looking at now, as the industry starts to mature, and particularly with the rollout of more mass applications, such as those involving transport, is the industry waking up to the opportunity of fiber optic cable and being able to take the decisions as to where best to put the fiber that they may be deploying for communications purposes, for example, and being able to then exploit it either immediately or at a later date. So we polled our members in 2017, and our members represent a significant but not total fraction of the fiber optic sensing industry. And we looked at the nature and range of installations that have been deployed. And we came up with over 1,000 and representing about 20,000 miles, 32,000 kilometers of coverage. And what is very clear there is there's some very strong sort of densities in China, where there's been quite heavy deployment of this technology. And in Central Europe, where it's been deployed very heavily for fire detection in automotive tunnels, for example. And then following that, the USA it comes with an increasing amount. The future perhaps is slightly different, and that's what we're going to look at in the second part of this talk. What is the potential for 1 billion sensors? So we have quite a few million sensors there. If we consider that 20,000 miles, 32,000 kilometers, where we equate a sensor to be roughly equal to around about 10 meters or so, 30 foot. That gives us quite an amazing number already deployed in an immature industry. Looking forward then to expansion, to adoption of this technology, where is it going to take us? So let's take an example from the US. There's about 250,000 kilometers, and forgive the imperial units, it helped keep things along one line, but an awful lot of distance of railroad in the US. Not all of it has fiber, but if a significant fraction of this already does have fiber, we have members with fiber optic sensing projects already on Class 1 railroads in the US. It's being heavily looked at. If at some point a significant fraction of this goes to fiber for some of the applications we've talked about, it represents clearly a huge investment in glass and in sensing potential. We can then extrapolate that to the rest of the world. Beyond the railroad industry, in the next slide, we can look at the road industry. And of course, there's a lot of roads in the US. It's a very dense coverage, 64 million kilometers worth of coverage. Not all of that would perhaps ever need fiber, and not all of it will be instrumented. Major trunk roads, shrinking down to main roads, possibly not the more rural roads, but nonetheless, massive potential for fiber optic sensing. What we see around the world at the moment within our membership is when new roads are going in, particularly trunk roads, they're generally going in with fiber in them for a variety of purposes. After roads is the oil and gas infrastructure. Now, oil and gas have been exhibited significant leadership in the adoption of fiber optic sensing for leak detection and theft prevention, as we've seen. In the USA, historically, fiber optic has not been deployed as the backhaul communications mechanism. It tended towards microwave. The rest of the world is more of a shared position. But nonetheless, 800,000 kilometers worth of pipeline already, more pipeline going in, some very significant projects awarded recently, fiber going on to them. And so they represent a major sensing potential. If we look even at one state, if we look at Texas, some data here from the Railroad Commission of Texas, who also look after the transmission of hazardous liquids and pipelines, a massive infrastructure in Texas alone of oil and gas, of which a lot of it is aging infrastructure. Questions of retrofit are very strong in people's minds. A lot of people looking at fiber and how it can be deployed on fresh installations or redeployed to existing installations. And finally, for the US, just the basic fiber telecoms infrastructure represents almost 1 million kilometers itself. That's just about getting data from A to B, but a lot of that could be repurposed for other reasons, as we've already seen. Particularly in the US, infrastructure tends to lie in corridors. So we will quite often find telecoms as infrastructure close to roads, close to pipelines. And just, we noted earlier the significance of China as a market itself for fiber optic sensing. We all know the level of expansion of infrastructure that has been in place in China and continues to be in place, with some predicted figures here, which come from public sources, of looking at the length of railroad at the moment of 127,000 kilometers, predicted to more than double by 2050, which is a massive growth. And as we've seen already, China is a very heavy investor in the adoption of fiber optic technology for sensing purposes. Okay, so the call for 1 billion sensors. Our talk here is about when it will arrive. The original call for 1 billion sensors came from Stanford University, Professor Biondi, who was looking at the potential of the existing telecoms infrastructure to build a 1 billion sensor array for observing earthquakes. They move through the ground very, very fast. And so we'll get the signatures from the epicenter very, very quickly, and within enough time potentially to shut down significant and expensive facilities which could be damaged. So we can make our signatures go at the speed of light, which is an awful lot faster than the speed of the earthquake moving through the soil and rock. And so there potentially is a lot of advantage if the fiber optic infrastructure of California was instrumented with fiber optic based seismic sensors. Do a search for the big glass mic to find an example of what the Professor Biondi is trying to achieve. And finally, from the map perspective, just the world map of deployed oceanographic fiber optic, or rather marine fiber optic cabling. And this is, of course, for internet-based transmission. This in itself affords quite a lot of potential for sensing, especially for areas that are seismic prone or high risk of tsunami warnings. We could use and exploit the fiber optic seabed infrastructure to again provide advanced warning, and there's a number of projects within our membership already looking at this topic. So there exists around the world globally a massive infrastructure of fiber optic cable. The question is, how is it going to grow, and how is that going to be deployed for fiber optic sensing purposes? When do we hit this 1 billion sensors? So the current market potential, if we look at how much we've saturated existing deployed fiber, it's not even at 1%. We've looked at the numbers of sensor coverage, the 22,000 miles we had in 2017, where we are now in 2019. And it's a very, very small fraction of the existing installed infrastructure base. So even within retrofit, utilizing dark fibers on infrastructure that exists already, if there's a purpose for it, which would never be 100%, there's still massive growth for our industry and massive potential to reach the 1 billion sensors. But it's not just as simple as that. If we go to the next slide, one of the key enablers that we see for fiber optic sensing is the rise of 5G communications. This is already noted to be essential for some of the planned advances in the movement to transport, fleets of vehicles running in autonomous modes, narrowing the gap between vehicles, the heavy level of positioning information, two-way flow of information and position. We're always going to rely on 5G, or we'll have a very heavy reliance on 5G, of which the backhaul technology for this is predominantly going to be fiber. And the graphs here are quite interesting. On the left-hand side, we're looking at the predictions of the data density per square kilometer in significant cities around the world. And a lot of this motivated by, or at least enabled by the 5G technology. On the right-hand side, we're looking at the backhaul mechanisms that are predicted. So in 2017, we're pretty much where we are now. Fiber plays a really key part, but it's a much more mixed modality with a lot of backhaul done by millimeter wave as well through line of sight. What is predicted through to the mid-2020s is an increase in the proportion that's carried by glass. So if glass is being put in to support 5G and put in near infrastructure, then the opportunities exist to be selective about the placement of this to enable it to be utilized for multi-purpose. So we can look to encourage the adoption of technology towards key assets of infrastructure, roads, railways, pipelines, etc., to allow the owners of the assets to make multiple benefits, to act as the backhaul for telecommunications, but at the same time, sensing abilities out of those fibers and self-protection of the integrity of the fiber at the same time. So we see this as a key enabler for many aspects of our joint industry. And then in my last slide, we look at where our billion sensors is going to arrive. We've looked at the growth curves, and it's a very immature industry at the moment, but we see this significantly rising with autonomous vehicles and 5G really pushing a lot of optimized adoption of this technology. We've done an awful lot of sweeping up easy to access projects where we can deliver a quick and easy benefit from an optimum and lucky positioning of fiber. As the dynamics of the industry move more towards deciding the best type of fiber, the best location of the fiber, placing the fiber in association with the desired applications, it opens up an awful lot more. And based on our concept of approximately a 10-meter sensor, those numbers varies depending on the job that's being done and the provider, the type of technology. We see this rise increasing, and we're hitting our billion sensors as a combined industry effort sometime in the mid-2020s. Now, as an industry forecast, it's of course wrong. As soon as I've put it down and committed it to paper, I'll look like a laughingstock in 2025. I'm pretty sure of that. One way or another, obviously we hope it is the earlier way. We've achieved this very early in the 2020s. But nonetheless, as a point of perspective of where the industry goes, we see significant growth potential well beyond the 1 billion sensors as this technology starts to be adopted for more and more uses. So I think that may be our last slide, Etienne. There we go. So I think we'll pass back to Mark at this point, shall we? And to host any questions that are coming in.
Thank you very much, Chris and Etienne, for a very informative presentation. If you have a question, you can put it in a text message in the box to the right, and I will relay it. Chris, I'm fascinated by the integration that you see with 5G and fiber optic sensing. Now, does 5G expand the reach? How do you see that being integrated, or is that something that drives the installation of more fiber?
Yeah, so 5G is got to be supported by backhaul technology. The data rates that the public are demanding and that industrial applications are demanding are only really easily satisfied by the fiber network. So we'll have a greater density of 5G sources relaying that data, but the backhaul for this is predominantly going to be fiber, as the data shows. And so the opportunity really lies as to where that backhaul is going to be routed. Can we do better than putting it through a plowed field where nothing is happening? It's easier to access that in places like, for example, railroad deployments where you're running 5G mechanisms close to the routings of people. So they could be running down railroads, they'll be running down roads, particularly in rural settings, or rather remote settings. And so then, instead of just taking the shortest path from A to B, can the industry move to look at putting the fiber in the optimum path to do something more useful, and thereby create an economic advantage from the deployment of the fiber beyond that which is achieved solely by the relay of the data.
That's helpful. We had a question about the rail, and is this something that can be used to, again, this integration can be used to track assets? How would that work?
So a number of our members are already doing that. We have a number of sensing companies within our organization who already provide fiber optic based train position technology. At the moment, it tends to be used for non-safety related activities, but I expect that will change in the future. But there's obviously a significant burden and lead time into high SIL related technologies. So right now, it's being used in a number of places, particularly in Europe and in the Far East, for doing train monitoring, and it provides a very accurate mechanism of knowing where the trains are, where the length of what the length of the train is, to quite a precise measure. It even works in tunnel where things like GPS cannot work, and so it's being used in specific locations for specific measurements and information sources right now. As the maturity of the adoption expands, this will go to more and more. So most of the time at the moment, the types of deployment are characterized by early sort of feasibility type approaches over the last 3 to 5 years, beginning to migrate into direct applications. And so the potential of having multiple applications hosted in a single technology in a fiber has been very attractive. So at the same time as doing train tracking, we can be looking at copper theft from the same trench, or we can be looking for wheel flats, or we can be looking for rail breaks. And this is very attractive to the rail industry. I think there's questions to be wrestled with as to what the commercial model that rail industries will finally adopt, who does what part of the problem, but it's a very exciting time to be working in fiber optic sensing.
Sure. Now, next question, are the current impediments to deployment coming more from lack of awareness from potential users of DFOS, or is it from the lack of public policies or investment policies to encourage deployment?
So again, that's a very good question. And it really reflects, I think, the first part of that, I think, back on why FOSA was created. A number of the founding organizations, of which my own and Etienne's were one, got together in 2017 to really try and hit these questions of education. If you've got one company waving a flag, it's interesting to the right people, but it's not an industry. The power of an association allows an independent message to be broadcast. And so that sort of industry outreach work is, I think, really half of the purpose right now is trying to educate people as to the benefits that can be achieved while they're thinking about the fiber optic projects. Public policy is, again, very much a key part. And that tends to be involved on some of our applications, such as, for example, pipeline sensing for leak detection that Etienne illustrated. Where these are governed by public policy. And I think it's fair to say that the education parts go hand in hand with the public policy parts. Etienne, do you have anything to add there?
Yes, I think that when we can establish a link with our technologies and the telecommunication world, it also helps. Very often we are being asked, but do you have a track record? Is it a new technology? Is there and ready? It's basically built around all the things that makes the internet happening, as Chris mentioned before, in the backbone. So it's there, it's reliable, it's known, has been around for years. And when people can make that link, and when we as Fiber Optic Sensing Association can establish the link between a technology that everybody knows about and what we are doing, I think it helps the technology on its own and the people to adapt it.
So the next question is I think an opportunity for some clarification. I know this is sometimes a misunderstanding. We've talked about existing fiber optic cable installation, that is for telecommunications purposes. Could you address the process or the opportunities for repurposing that existing fiber optic infrastructure for sensing?
I think what we can say is that if there is a fiber installed somewhere, that fiber potentially is a sensor. So if the fiber is close enough from an asset, then we can get valuable information from the asset. I think that's a way of understanding how we can use existing installation and existing optical fibers to move towards a sensing system and a valuable sensing system. Then if the fibers is far away from what we want to monitor, then there is no coupling between the asset and the position of the fibers, and there is no measurement, and that's the limit between using or having an existing fibers and an existing installation and do some sensing.
I think that's probably a really key takeaway for this particular presentation, is just the a potential for that existing infrastructure to be repurposed. And did you want to add something to that, Chris?
Yeah, I was just going to add that the actual intimate process of hooking up to the glass, generally people have the impression that we're trying to work on a cable that is already doing another job. So the cable might, but generally when people put a fiber optic cable into the ground, it's got multiple fibers in it. So typically these are in the hundreds, something like 168 fibers in a cable that's maybe an inch or less across. And so whilst it may be possible for our members to deploy their technology on a fiber that is already being used for data transmission, it tends to be unappealing because you have to separate out the signals into different wavelengths, different colors of light, and there's an obvious interruption of service while you're doing that. So whilst technically it's feasible, you have to jump through a lot of hoops, but it's very rare that this actually occurs. In most circumstances, there's a dark fiber. By dark fiber, we mean one that's unused on either side. They're just sitting there as spare fibers waiting for application. By taking one of those, that's normally the simplest and easiest option to be able to deploy the technology. And then you're faced with Etienne's questions of whether you can do a viable job or not.
Thanks. A follow-up to that question is how difficult is it to find spare fiber in an undersea cable?
So there's been a big push over the last sort of 5 years to soak up an awful lot of fiber. And so the efforts of the big data companies, Google particularly, they've been saturating a lot of fiber. They found it somewhat easier to, in many cases, to go and relay new fiber. So I know some of our members have been doing work on subsea cabling, and it'll vary depending on the cable. But you can see from the density of the cabling in each region, I don't think we're ever really talking about one cable coming ashore in a specific location. And so there still is capacity. It's very closely managed, and there's always this running battle between how many fibers do you deploy for a given transport technology, the core backbone and the speed of that data transport, before it then becomes more efficient cost-wise to add another zero to your transport technology. It's obviously going to be limitations to that. You can't keep adding zeros before you need a new technology. But we're still in that situation where fibers are often being repurposed by the next generation of data transport technology. And so it hasn't really reached a case of all the fibers are full and there's nowhere to go. At the end of the day, it's always an economic argument, and the movement of data has a lot of economic power behind it. So when the fibers run out, new cables do get deployed.
You've touched on a number of the autonomous or autonomous vehicle or transportation related uses. Could you comment on the availability of fiber along highways, and is that something that perhaps some public policies can help address?
So I think that's very sorely needed, both as an outreach and a public policy exercise. From the members that I know that do road-based projects, they are very opportunistic in terms of, okay, we've got a fiber running down the road, we're using it for smart motorways, or we're using it for communications, for example, to our cameras to relay the signals. The use for fiber sensing has generally been an afterthought, and the types of projects that are being deployed on roadways are generally pilot projects where people are exploring them to see what they can do in terms of vehicle counting or journey time management, queue detection, etc. I think once that phase is completed, which will be over the next 2 to 3 years, we'll then start to see an interest in where should I have my fiber? Do I have to retrofit it? So I would say that quite often the fiber is not always in the optimum position, but one of the benefits of the fiber optic sensing is that it doesn't have to be in the optimum position for the full length of its deployment. As long as there's enough that is running within an acceptable coupling range, as Etienne was discussing, then you can use those sections for your measurement, and you're extracting something with a high level of overview from that. So it doesn't necessarily need to run within spec for 100% of the length.
And I think this will probably be our last question, but it was a question about the requirements for field service providers. And can you comment on the need for training for operators, for technicians, in order to assist with the testing, measurement, troubleshooting, and maintenance of the fiber?
I think what we've seen is that in terms of installation, it's very close to what is done for the telecommunication people. So if we come to the field and explain to the people that they have to look for a few specific points to help for the sensing, then usually things are going quite well without any problem. When it comes to the configuration of the instrument, that is obviously something that belongs to us as a supplier, and the operation again requires normally little training, because the type of data that we provide is either a traffic light, so it's working fine, or you have an issue somewhere with the localization, or something maybe a bit more complex, like there is a train in this position or a fire in the tunnel. But usually the way we provide the information to the operator, and the type of information for the operator is something easy to understand and easy to handle. So it's not really more difficult than any fiber optic related job.
Well, thank you both. I think that brings us up to the top of the hour. I know there's always the question we have of when will the full presentation be available, and it should be fairly quickly, within probably the next 24 hours, if not less, both on the FOSA website, Fiber Optic Sensing Association website, but also specifically on our YouTube channel. And I know that quite a few people avail this material through those two channels. Thank you, Goat, for a very interesting presentation. This will be our last webinar until September, but be paying attention as we announce our schedule beginning in September. Thank you both for a very informative presentation. And that concludes this webinar.